Hi everyone, welcome to part 1 on our video recordings for section 2.4 dealing with infinite limits. In this set of videos, we're going to be discussing infinite limits and how they relate to vertical asymptotes. Alright, so let's go ahead and begin. Okay, so let's say that we're given the following limit and we want to see if it exists. So we have the limit as x approaches 0 for 1 over x squared. Alright, so now, just as we've been doing in class, I want you guys to plug in small values for x to see what you get. Do these values approach a single number? Well, let's go ahead and do the following tables. Let's see what happens as x approaches 0 from the right, in other words, values for x being greater than 0, and what happens as x approaches 0 from the left, in other words, values for x that are less than 0. Alright, now at this point, I want you to plug these values into the calculator and see what you're getting. So please pause the video and let's compare our results. Alright, so these are the values that I got. Now, when x was approaching 0 from the right, we got to see here that this time around, the y values were approaching infinity. So yeah, we saw that when x was 0.1, we got 100, but when x was 0.001, we actually got 1,000,000. So if the x got even smaller, then the y's would have gotten even larger. And that's exactly what's happening here as you approach 0 coming in from the left. We get to see here that, okay, as the axis approach 0 from the left, the y values approach infinity as well. So what would this tell you? What is the limit as x approaches 0 for 1 over x squared? It's going to be infinity. Now let's go ahead and take a look at the intuitive definition of infinite limits. Let's say that we have a function f to be defined on both sides of a except possibly at a itself. Then the following equation, the limit as x approaches a for f of x is equals to plus or minus infinity, means that the values for the function can be made to be arbitrarily large, either in the positive or negative direction, by taking x values sufficiently close to a, but not equals to a. Now, if the limit as x approaches a for f of x is equal to infinity, this is going to be true if and only if both one-sided limits also approach infinity. Very similar to what we were discussing in class. Remember, if the limit exists, it must mean that the one-sided limits approach the same value. Now, I do want to clarify here that this does not mean that infinity is a number or that the limit exists. It's just simply a way of describing how the limit does not exist. It's still telling us behavior about the function as x approaches a number. Okay, so now let's take a look at a couple of examples. Let's see if we can evaluate the limit as x approaches 2 from the right of 4 over x minus 2 and the limit as x approaches 2 from the left of 4 over x minus 2. Alright, so let's begin with the limit as x approaches 2 from the right for 4 over x minus 2. Now remember, anytime they're being asked to evaluate a limit, I want you to use direct substitution. But if we use direct substitution here, well, we would get a 4 divided by 0, and that would be a problem. In this case, direct substitution doesn't work. But that's fine, because remember, ultimately, well, we're not plugging in 2. We're trying to see what happens as the axis gets closer and closer to 2, coming in from the right. So this is how I want you guys to think about this problem. I'm going to go ahead and create a number line here. And I'm going to put the value that we're getting closer and closer to in the x. So let's say that we have a 2 right over here. Now, because we're getting closer and closer to 2, as close as we're going to get, I'm going to put in here a couple of values that are not going to be up to scale, but hopefully they get the picture across. So let's say I have a 2.1 here, then I can get closer, let's say a 2.001, and like right over here, let's say it's a 2.0001. All right, so what is happening to the fraction 4 over x minus 2 as the axis gets closer and closer to from the right? Well, this is what's going on. Let's go ahead and put in a 2.0001. So I'm going to have a 4 over a 2.0001 minus 2. Now on the denominator, you get to see here that we're basically going to get a 0.0001. And now it's very similar to the first problem here. What would be 4 over 0.0001? It's going to be like about 4,000. But the thing is, well, I chose here the 2.0001, but really I could have gotten closer to 2 if I wanted to. Remember, we can get as arbitrarily close as we want. So in essence, what's happening here is that you're dealing in a situation where we have 4 divided by an arbitrarily small positive number. And this is what's happening with the limit. The limit, as x approaches 2 from the right, for 4 over x minus 2, well, it's going to be 4 over an arbitrarily small positive number. And we know that a constant divided by an arbitrarily small positive number is positive infinity. So there we go. Our limit here is actually infinity. Now I want you guys to think about what would be the limit as x approaches 2 from the left for 4 over x minus 2. Is it still going to be infinity? Are we getting still an arbitrarily small positive number in our denominator? Or is it something else? I want you guys to try this one. So pause the video here and see if you can come up with an answer. Well, if your answer here was a negative infinity, you'd be absolutely correct. Now, why did we get the negative infinity here? Well, that's because this time around, we're getting closer and closer to 2, but since we're coming in from the left, from values of x that are smaller than 2, you can think of, let's say, getting a 1.999, and 1.999 minus 2 would have been a negative 0.001, but if we got even closer to 2, this value would have been even smaller, so then we'd be dividing by an even smaller number, so our fraction is actually getting bigger and bigger. All right, perfect. Now, let's go ahead and see an application for infinite limits. And it's an application that you might remember saying in a pre-calculus course. And this one here is vertical asymptotes. Here is the definition for a vertical asymptote. The vertical line x equals to a is called a vertical asymptote for the curve y equals to f of x if at least one of the following statements is true. The limit as x approaches a from the right for f of x is plus or minus infinity. The limit as x approaches a from the left for f of x is equals to plus or minus infinity, or the limit for f of x as x approaches a is plus or minus infinity. So in other words, as long as you get an infinite limit as the x approaches a number, you are dealing with a vertical asymptote in a curve. Okay, so let's see how many vertical asymptotes does the following function have. So if we have the function f of x equals to x squared minus 4x plus 3, and it's all over x squared minus 1. All right, so what would be the vertical asymptotes, if any? Now, I do want to verify the work here with a graphing utility. You guys can verify it with your graphing calculator, but because I'm recording, I'll be verifying it on Desmos, guys. All right, so let's see. What would be the limit as x approaches 1 for f of x here? All right, well, let's see. Now, as usual, anytime that we're trying to evaluate the limit, we go ahead and use direct substitution. So if I plug in 1 for x, then on the top I would have 1 minus 4, which is negative 3 plus 3. Okay, we're getting a 0, which again, it wouldn't necessarily be a problem. But if I plug in 1 in the denominator, well, I'm also getting a 0. So we got 0, 0, and indeterminate form, which, what did that mean? More work. Now, what do you think the more work in this case means? Well, you probably guessed it. We got a factor. So these are the factors that I got. We got the limit here as x approaches 1 for x minus 1 times x minus 3 all over x plus 1 times x minus 1. And the good news is that I do see some terms that are going to be canceling. I can get to cancel the x minus 1, both top and bottom, and what we're left with is the limit as x approaches 1 for x minus 3 over x plus 1, which is going to give us here a negative 2 over 2, which is equals to a negative 1. Okay, well, we're not getting infinity here, so it seems like we do not have an asymptote at 1. But now I'm a little bit curious. Is that okay? Is that normal? Because, and this is a throwback to pre-calc, maybe some of you guys remember that whenever you were looking for vertical asymptotes given a rational function, or a rational expression, they told you to set the denominator equal to 0 to see what was the vertical asymptote. But right now, well, if we set the denominator equal to 0, well, we get to see here that a solution here would have been x squared is equals to a 1, which would have given you two answers, x equals to a negative 1, and x is equals to a 1. But the thing is, well, this is not matching with your definition in pre-calc. Because right now, we're saying here that the limit, as x approaches 1, well, we get a y value of negative 1, not infinity, so x equals to 1 is actually not a vertical asymptote. Now, did they lie to you in pre-calculus? Not really. This method would work, setting the denominator to 0, would work to find the vertical asymptotes, but it's only after you simplified the rational expression or the rational function. Now, the reason I brought this up, guys, is because we're not in a pre-calculus course anymore. This time around, if I want you to find vertical asymptotes, I want you to prove and show that they're vertical asymptotes by getting an infinite limit. Okay, so now let's take a look at another example here. It's the same type of problem. We're dealing with the same function, but this time around, we're taking the limit as x approaches -1, specifically from the left. All right, so if I go ahead and take the limit as x approaches -1 from the left for the function using direct substitution, and I'll put it here, direct substitution, well, we would have actually gotten a 0 or 0 again. Okay, so it meant more work, which means we have to factor, but the good news is that we already had the factors here. We already saw what canceled. So what we're trying to do here then is find the limit as x approaches -1 from the left for x minus 3 over x plus 1. All right, now, if we go ahead and use direct substitution like we did above, well, we'd be running into trouble because we would have gotten a -4 divided by 0. And look at that. Now this problem here is not all that different to the one that we tried here with example 1. All right, so what do we do here? Well, think about what's happening on the denominator as the x gets closer and closer to -1. And again, guys, the focus here is on the denominator because this is the one that is approaching 0. The numerator has no problem. The numerator approaches 4, and that's okay, not an issue. It's just that since we cannot divide by 0, we want to know what is happening as our denominator gets closer and closer to 0. All right, so just as we did in example 1, I'm going to go ahead and create a number line here. And this time around, we are approaching a -1. So I'll put the -1 right over here. All right, now we are approaching -1 from values that are less than 1 since it's from the left. So a value that's less than -1, I'm thinking here of maybe a -1.001, just to get the point across, even though we can get closer and closer and closer. So let's see, this doesn't work, but, and I'm going to focus just on the denominator right now, if I have a -1.001 plus 1 in my denominator, and again, I'll just leave the top here, I'll leave a -4, it's a constant, you can just put it as a constant as well. But what we have here then is a -4 divided by, now it's going to be a -0.001. Now, if we got even closer and closer, well then, our denominator just becomes an arbitrarily small, but an arbitrarily small negative number. So, I'm going to go ahead and write it here. When we're finding the limit, as x approaches -1 from the left for x minus 3 over x plus 1, what we're going to get here is get really, really close to 4 on the, -4 on the numerator, and in the bottom, we're going to have here an arbitrarily small negative number. Now, last thing to note here, and be extra careful, right now, will I be getting a positive infinity or a negative infinity? Well, on the numerator, I have a negative number, but on the denominator, I also have a negative number. So we have we have a negative divided by a negative, which gives us a positive. So that means that we are getting a positive infinity. So now we have an infinite limit. So that means that we do have a vertical asymptote, which I'll abbreviate here as VA. We have a vertical asymptote at x equals to a -1. All right, now, I did say that I was going to verify it here on a graphing utility, in my case Desmos, but I just want to mention here that we do have another problem. We're asked here what would be the limit as x approaches -1 from the right for that same function. Now this one here, I'm not going to do it because we just already showed that -1 happens to be a vertical asymptote for the function. So we can expect this particular limit to be either a positive infinity or a negative infinity. But let's see which one it would have been on the graph. All right, so here we have the graph on Desmos, and we get to see that indeed the x equals to -1 is a vertical asymptote for this particular function. So great, we found the vertical asymptotes. Now, I do want to make another comment. When we were talking about the pre-calc material or the review, well, we said that, hey, at x equals to 1, it wasn't quite a vertical asymptote. We're actually getting a -1. But remember, the -1 is not the value for the function. That was the limit. As the x got closer and closer to 1, the y values got closer and closer to -1. It is still true that when you plug in 1 into the denominator, you get 0. So Desmos here is not actually giving you the accurate graph. It should have been like this. There we go. We should have had a hole or an open circle right over here when x is 1. The y value to get closer and closer to is -1. But the function is not defined at 1 nor at -1. It's just that one of them is an asymptote, the other one is just, as we'll see later, a discontinuity. Alright, perfect. So now let's take a look at a couple of more examples. Alright, so for example 3, we want to see if we can find out what would be the limit as x approaches pi over 2 from the left for the tangent function. Now, I'm going to go ahead and work on this problem in different ways, although both of them would be relying on knowing how the graphs of functions look like. Alright, so let's go ahead and pause the video, and I want you guys to think, hey, how did the graph of the tangent function look like? Alright, so you remember that the tangent function looks something like this. Now, once we have the graph, it's a lot easier to figure out what would be the limit. Alright, well, if I'm approaching pi over 2, coming in from the left, what is the limit? What are my y values getting closer and closer to? So if we follow the graph here, we trace it, well, it seems like our limit is going to be infinity. And that'd be all. If you guys remember the graph and you make the argument using the graph, that's perfectly fine. I'll give you full credit. Now, what if we do not know the shape of the graph though? Well, that's okay. We can do it a slightly different way. Now, in order to do that though, we do need to remember certain trig identities. So, how is the tangent function defined in terms of sine and cosine? Well, you may remember that the tangent is the same thing as sine or cosine. Alright, well, how can that help us? Well, if we're evaluating the limit here, what we can do is rewrite the tangent in terms of sine and cosine, and then find the limits for the sine and the cosine individually as x approaches pi over 2 coming in from the left. Now, you may recall here that the sine of pi over 2 is just equals to 1, but here's a little bit of a problem. Well, what about the cosine of pi over 2? Well, that's a 0, unfortunately. Uh-oh. So we're kind of back at where we were starting at the beginning of class. Okay, we're dividing by 0, but not really. We want to see what's happening as the x's get, well, in this case, as the denominator is getting closer and closer to 0. So for this one here, I'll take the opportunity to remind you how the graph of a cosine function looks like. There we go. This is the graph of a cosine function, but I'm only going from 0 to 3 pi over 2. Alright, so what we're trying to find out here is, okay, well, as the x gets closer and closer to pi over 2 coming in from the left, right, so we're coming in from the left, what are we getting closer and closer to? Well, we are indeed getting closer and closer to 0, but remember, we're valuing the limit, so we're getting closer and closer to 0. So in other words, when you're valuing the limit for the sine over the cosine as x approaches pi over 2 from the left, what we actually have here is 1 over, and you probably know what's coming next. It's an arbitrarily small positive number, which means that overall, the ratio here, the fraction, is going to be approaching infinity. Alright, so this is two ways of figuring out the limit for this particular problem. Alright, now let's take a look at the last one. Now this last one here is asking us to figure out, well, what would be the limit as x approaches 0 from the right for the natural log function? Now this one here, I'm going to go ahead and make another argument for the limit being, well, in this case, negative infinity through the use of the graph, because unfortunately there's not a lot of algebra that you can do. The next best thing that you can do is maybe plug in values in the calculator, but I do want you guys to know the shapes of graphs. So I'm going to go ahead and make a sketch here for the natural log function. Alright, so this is a sketch here for the natural log function. Now, here we have the 1, the element of 1 is 0. Here we have the x value of 0. All right, so what is happening as the x's get closer and closer to 0? What is your y value getting closer and closer to? Well, if we go ahead and follow the graph, we trace it, we get to see here that we're heading all the way down to negative infinity. So this particular answer here, the limit as x approaches 0 from the right for the natural log function is negative infinity. Okay? Alrighty, so this concludes our lecture on infinite limits. Now, I thought I was going to put it in multiple parts, but overall the video wasn't too long, so I'll just keep it here as part 1. However, I'll see everyone in the next recording dealing with limits at infinity. See you guys there.